Okay, and now we can start with the official part. It is my great pleasure to introduce Professor Roman Słowiński from Poznań University of Technology and Systems Research Institute in Polish Academy of Sciences. It's a great honor, Roman, to have you here with us. Professor Słowiński has a lot of achievements. I'm not going to mention all of them. Of course, from my perspective, his achievements in the theory of rough sets are very important. But even more importantly, Professor Słowiński has extremely important results in operational research and decision aiding. He's been editor-in-chief of European Journal of Operational Research for many, many years. And he received a lot of awards, prizes. He is distinguished professor in many places, so this is really fantastic to have you here. Roman, the floor is yours.
Thank you very much, Dominic. Good morning, still good morning, ladies and gentlemen. It's a great honor to be in front of you, and I'm grateful to the organizer for inviting me to give this keynote speech. Of course, they took a risk because you are a very diversified population, and your background is very difficult, so I may completely fail. The subject of my talk today will be about decision aiding, which is I think an important field of computer science, because if computers would not serve to help make better decisions, for what they would exist? So please allow me to present my point about decision aiding, where is the challenge. I will try to convince you that the challenge is in solving multi-dimensional decision problems, and among the dimensions may be many conflicting criteria. So I will speak about multiple criteria decision aiding, and I will show its evolution, because this is a subfield of decision sciences which is older than 60, 70 years. And it is living an evolution with artificial intelligence. The main approach that represents these trends is called robust ordinal regression. Then I will finish with applications, examples, just a few examples, and with summary and conclusions. So, of course, to be didactic, I will have to be a little bit superficial. Please forgive me if I will not go into details of any point. So where is the challenge? When we speak about decision problems, we have in mind an objective or objectives to be attained, and there should exist many alternative ways for attaining these objectives. They constitute a set of possible actions, sometimes called alternatives, solutions, objects, acts, etc. And the questions which are imposed with respect to the set of actions may be the following in general. How to choose the best action? How to classify actions into some predefined decision classes? Or how to order actions from the best to the worst? So graphically, these problems could be represented like this. The choice is the selection of the most important and most interesting, sometimes diversified, non-comparable actions, and we do not care about the order of the rest. Classification, which is shown here, this is the ordinal classification because classes are ordered from the best to the worst, consists in assigning one action to each to one of these classes. And the ranking or ordering is the ordering from the best to the worst, not always the total order, because sometimes actions are non-comparable and we have to be satisfied with partial order. Then, having in mind those three kinds of problems, we have to admit that those decision problems are multidimensional. And these multiple dimensions may come from many sources. And the sources which are very distinctive are, for example, the presence of multiple decision makers, multiple voters. This is typical for group decision making. There may be also many conflicting points of views, defining different criteria of evaluations. And finally, there may be many possible states of the world with known or unknown probability and with different probabilities of outcomes. These three sources of multidimensional decision problems in the mid-20th century gave birth to three big subdisciplines of decision science. These are social choice theory, multiple criteria decision aiding, and decision under risk and uncertainty. Even if the language, the terminology of those subfields are different, the methodology is very similar. In fact, if you look at the basic elements, so the elements of A actions are sometimes candidates, sometimes acts of investment. Dimensions may be voters, criteria, probabilities of outcomes, but the only objective information that stems from the formulation of such multidimensional decision problems is dominance relation. In case of risk and uncertainty, this is stochastic dominance relation. To convince you, I give a very simple didactic example of theory of social choice, multi-criteria decision analysis, or aiding and decision under risk and uncertainty. I chose only two dimensions. So we have two voters, and the position of candidates A, B, C are coded 1, 2, 3. And you see that candidate C is dominated by B. And B and A are not dominating each other. So C can be eliminated from the consideration of the best, or in the ranking it will not be for sure the first. But A and B are non-comparable. When you take a multi-criteria decision analysis and you have three actions evaluated on time and cost, again 1, 2, 3, again C is dominated by B. And finally, when we have decision under risk and uncertainty, we have, of course, to maximize the probability of getting again at least G1 or at least G2. G2 is greater than G1, so the probability will not decrease. And as we have to maximize probability, we see that C is again dominated by B, but A and B are non-comparable. So dominance relation is something objective. However, it leaves many actions non-comparable. So in order to solve one of those three problems, we have to enrich the dominance relation using preference information. And here enters some subjective information, because this preference information should be provided by the user, by the decision maker. So for this reason, some mathematicians say that until now, those three problems were so-called ill-posed problems. To solve them, we need extra information, and this is preference information elicited from the decision maker. Based on this input of preference information, we can then learn or build a preference model which aggregates the multiple dimensions on which the actions are evaluated. And then we get a preference model which is inducing a preference relation on the set of actions, which is richer than the dominance relation. It makes simply actions more comparable. A proper exploitation of this preference relation will then lead to a required recommendation. So you see that in decision aiding, we have three distinctive steps: preference information elicitation, learning or building a preference model, and then exploitation of the preference relation induced by this model. In my talk, I will concentrate on multiple criteria decision aiding, although this methodology is the same for theory of social choice and for decision under risk and uncertainty. Let's start with aggregation. To aggregate multiple dimensions into one, we have in science now three possible ways. The first and the oldest is multiple attribute utility theory. So it suggests to synthesize the dimensions into a real valued function and to give each action a score. So, for example, this could be a weighted sum score or more advanced additive aggregation. And if criteria are interacting, then Sugeno or Choquet integral. Choquet for cardinal criteria and Sugeno for ordinal ones. The second possibility is through a binary system of relation, and the most famous here is outranking relation, which is grouping indifference, weak preference, and strict preference, and says simply A is at least as good as B. I will return to characterization of this relation later. And finally, there are also logical statements in forms of if-then decision rules. The decision rules, as you will see later, are induced from observation of holistic decisions. They have different syntax for classification and for ranking and choice. Why? Because in classification, the decision about assignment of an action to a class depends only on some reference profiles, here Ri, Rj, etc., which are induced from data. And in choice and ranking, a position of an action in the ranking depends on the comparison of the candidate with other candidates. So there are pairwise comparisons in the condition part of such rule, and intensity of preference for a pair is induced from data. And of course, when this third kind of models appeared, the question was which one is the most general? And the answer can be provided at the most basic level, axiomatic level, which will show where is the weakest assumption that permits to represent preferences using the given model. And the answer of this theorem says that the most general is rule representation of preferences. Now, a few words about the interest of operations research in multidimensional problems. You know that when, after the Second War, operational research developed, it was concentrated on optimization. Mathematical programming developed a lot, and on the side of aggregation of multiple dimensions in decision under risk and uncertainty, multi-attribute utility theory. However, a decision maker seldom has a single clear criterion in mind, and usually the points of view generate criteria which have heterogeneous scales, so finding a common unit for all of them is not easy. Moreover, by making a family of criteria explicit, so this multiple criteria decision aiding approach preserves the original concrete meaning of the corresponding evaluations by each actor, without resorting to some prefabricated conversion. And today we have to admit that there is no univocal point of view on this kind of scientific decision aiding. Very important trend in aggregation is so-called composite indicators, which appear in economy, in medicine, also in food sciences. You have heard about the Nutri-Score, or the index of sustainability, or livability, of comfort, etc. So these are very simplistic aggregations of very heterogeneous aspect into one score, ordinal or numerical, which is very dangerous to stay with them. To convince you that aggregation to a single dimension is dangerous, let me use the example of a paradox which is coming from the community of multi-attribute utility theory. When building a utility function which will represent the attitude of decision maker to risks, is he or she risk averse or risk prone, people are using comparisons of lotteries. So this is this preference information. And imagine that during such a test, two pairs of lotteries were presented, and the first one offers gaining $55,000 with probability 33%, 48, 66, 1, 0. And on the other hand, we have a certain reward which is 48,000. In the second, there is 55,000 with probability 33, the rest is 0, and on the right we have 48,000 with probability a little bit higher, 0.34. So how do you think, how people choose among those lotteries? The usual response is like that. People prefer sure things. However, the multi-attribute utility theory is based on the axiom of linear utility with respect to probabilities. And if you apply this formula, then we get a paradox, because in the first case, the inequality would be reversed comparing to the second one. A great advocate of multiple criteria decision aiding in Europe used to be Bernard Drouin, professor of the University Paris-Dauphine, who founded, we can say, a European school of decision aiding. Bernard, he published the famous book, Méthodologie multicritère d'aide à la décision, which starts with a hypothesis that decision aiding takes place in the context of imperfect knowledge and indetermination. So he says, among other things, that the models which are used to provide recommendations are ideal mathematical models which represent the reality with great approximation. He says the map is not the territory. The system of values is imprecise, incomplete, fuzzy, influenceable, and decision maker providing preference information hesitates, is unstable with expressing preferences. So the preference information, so this what comes to build the preference model is inconsistent, vague, and ambiguous. Further, the critics of Bernard Drouin with respect to multi-attribute utility theory start by observation that utility function, or real valued function, permits only to distinguish two situations, either preference or indifference. And moreover, the preference is asymmetric and transitive, and indifference is symmetric, reflexive, and transitive. With the transitivity of indifference, there is an obvious trouble. If you would have objects which are evaluated on a criterion such that they would be in a sequence of very similar objects, then by transitivity you would come to the paradox that the first is indiscernible with the last one. So Bernard is proposing to introduce a threshold, a function with threshold which would distinguish preference and indifference. And moreover, there would be another threshold, preference threshold, which would bring a zone of weak preference. And finally, he claims that in modeling preferences, we should be able to model incomparability. So how to do it? He proposed to equip the criteria with threshold, and such a criterion is called pseudo-criterion. Moreover, this outranking relation, which looks very poor because it says only action A is at least as good as action B. Remark, however, that when you will construct outranking relation for AB and for BA, then you may distinguish large preference, indifference, and incomparability. So this is what we expected. Now a few remarks about evolution of multiple criteria decision aiding towards artificial intelligence. When you observe the evolution of operations research and also our subfield of multi-criteria decision analysis, or AD, we can state that until 80s, this subfield developed according to, we would say, a model-centric paradigm. So this means that first we invent what will be the model of preferences, and then we try to convince the decision maker to provide us the parameters of this model. Then in 80s, personal computer entered into game. In 81, it was the Person of the Year of Time magazine. So personal computer permitted interaction, trial and error game. So this is more human-centric, we would say. And in 21st century, we have a lot of data about human choices. So these are holistic preference information first, and from this information, we try to build models. Now this is the paradigm of artificial intelligence. Show me your actions, and I will show you the model according to which you are acting. So this is more knowledge-driven. So this is maybe this last stage of development favorized the appearance of decision rule model in the aggregation. So I almost answered the question how the preference data should be elicited, either direct or indirect. Direct, which existed until 80s. I am giving here an example of an article by Peter Fishberg, one of the pillars of decision theory, which in '67 already wrote about 24 methods of estimating additive utilities. So this means that this is not just like that we could express weights for a weighted sum. And if this is not a weighted sum, but more complex additive or outranking relation, we need even more parameters, which is cognitively very difficult for decision makers. So, indirect, through holistic judgments, decision examples. And this is a relatively easy preference information. It can be gathered without active participation of decision makers, which is sometimes unpleasant for us because we are observed. However, the psychologists confirm that decision makers are more confident exercising decisions, or showing examples instead of explaining them. When we speak with medical doctors, very often they say, okay, so this is a typical patient of disease A. And if you ask for explanation, it does not come very easily. In economy, we have examples of predecessors. For example, Samuelson, before the Second War, he wrote about revealed preference theory. And of course, we have learning from examples paradigm in artificial intelligence and machine learning. So the conclusion is indirect elicitation of preferences is more user-friendly. How they can be expressed, those holistic judgments. In our case, this can be either comparisons of vectors of values, and if somebody is confused with numbers, it can be a comparison of ideograms of the actions, and behind those symbols there are precise evaluations. This could be also examples of typical objects, acts in class medium or good, and also this could be even intensity of preference, but not necessarily cardinal, like some method requires. But A is preferred to Z more than C is preferred to K. Note that A is preferred to Z 3 times more than C is preferred to K. And how to deal with holistic preference information expressed in those terms. So, historically, the first method that permitted such an ordinal regression realization is called UTA. It is also a method which was proposed in France in the same laboratory as Bernard Roy worked. Eric Jacques-Lagrèze and Jean Siscos, they proposed a method which, very shortly speaking, is based on the following idea. We have a set of actions which is very huge. For example, on the market we want to buy a car, and there is 1,000 types of cars. And in this 1,000, there are probably few cars which we would be able to compare. And say, car X is better than car Y, Z than W, etc. So these are those pairwise comparisons in the middle. And then mathematicians, analysts, could ask the question, am I able to find a value function which is able to reconstruct these pairwise comparisons? Value function or outranking relation or decision rules, but later. First, it started with value function, with deterministic utility function. And if this is possible, then this real valued function can be used to all 1,000 actions, and they are, according to the real value, ranking the actions from the best to the worst. This approach was proposed for additive value function with piecewise linear marginal value functions. The characteristic points of piecewise linear marginal value functions can be found using linear programming. So even if it is not totally linear. And now I will pass to a small example to be a little bit more didactic. So we take data from Economist Intelligence Unit, which wish to rank countries with respect to digital economy. And I took 17 countries, evaluated on 6 criteria with the scale from 0 to 10. And their performances are just vectors of those 6 values. So if we would use the UTA method directly to this example, then the marginal value functions, which are shown here from 1 to 6, would rank the actions as the decision maker wished for 3 pairs. Sweden before Denmark, UK before Malta, and France before Bulgaria. So this is the preference information. Only 3 pairwise comparisons on the left. Yes, and the additive value function of this form is ranking everything. However, this is not the only compatible additive value function. There are many more additive value functions, and the danger is that they will rank the actions in a different way. Even if they will keep the ranking of Sweden, Denmark, UK, Malta, France, etc., as decision makers wished in this preference information. So, in fact, we have to cope with infinity of compatible instances of the value function. And this is why we proposed so-called robust ordinal regression. And in this scheme, the only difference is that we will use all instances of the compatible preference model, and we will apply all instances on the thousands of actions. And what will be the result? The result for each pair will be possible and necessary. The relation for a pair xy will be possible if at least one instance is giving advantage to x over y, and necessary if all compatible instances are giving advantage of x over y. The possible relation is complete and negatively transitive, and the necessary relation is a partial preorder. So, I explain again graphically that for a given set of pairwise comparisons, using linear programming, we are able to define constraints through which a monotone, not only linear, but monotone increasing or decreasing marginal value function will pass and will give a compatible instance of the value function. And then the necessary ranking will be true everywhere where there is a pairwise comparison from the beginning, and some other actions will also enter into necessary relations. When we increase the number of pairwise comparisons, like now, the area of possible variation of monotonic marginal value functions is decreasing, because this is like a new constraint that is added to the set of constraints, and more actions are in the relations of necessary relation. And this process evolves from dominance relation, where there is no pairwise comparison, to complete order. Of course, the decision maker may stop at some moment when the ranking is conclusive enough to make a decision. So if we would apply this approach of robust ordinal regression to our example, then we would see that some actions, some countries, for those three pairs of pairwise comparisons are comparable, but others not. And this is more fair recommendation, more fair result. So robust ordinal regression works in a loop of constructive learning. And this is robust because it takes into account partial preference information. Thus, this preference information that is not too cognitively not too hard for the decision maker. So this methodology is very similar to preference learning in machine learning. However, we do not use the statistical criterion of a loss function to find the compatible instances. So here is the formulation of the linear programming to find compatible instances, and here again another formulation of linear programming to check if the relation is necessary for A and B or possible. So these are relatively easy and not so huge linear programming problems. What if we cannot find additive value function which will reconstruct the pairwise comparison? It is possible, of course, because even if the decision maker will not violate dominance, it is possible that some pairwise comparisons are not representable but by additive utility. So we can find such pairwise comparisons which are troublesome using 0-1 programming, or we can continue if the error is not too big. Or we can switch to a more complex value function, for example, Choquet integral in case of cardinal utilities. With the robust ordinal regression, an interesting possibility is to make analysis of extreme positions of actions in the ranking. I will not have time to explain in detail, but using, I think, wise trick with 0-1 variables and so-called big M, we are able to find extreme positions of countries, like here, for the preference information that we currently have. Yes, so Sweden may be third, but maybe also third, etc. Another possible analysis is stochastic ordinal regression. So this is useful when, at the early stages, the necessary relation is poor. So then we can sample compatible instances of value functions and check at the time if A is preferred to B and what is the position of A in the ranking. In this way, we get the pairwise winning index or the rank acceptability index. And for example, we will learn that A is preferred to B with probability 20% and vice versa 80%, etc. It is very important to be able to consider also a hierarchy of criteria. Hierarchy is permitting to decompose complex problems into layers of criteria of different level of generality. And in such a case, it is also reasonable to consider the preference relation in each node of the hierarchy tree. And the preference information could be also related with some node with some criterion on a lower level, not only at the root of the tree. For example, we could say that if mathematics, for example, in the evaluation of students is divided into algebra, geometry, etc., so we could say that on algebra, student A is better than student B. Yes. So the information about pairwise comparison can be partial. And also intensity of preference A to B is preferred at least as much as C to D on algebra, on chemistry, etc. So, of course, necessary and possible relation have here a little bit different properties. We apply this for other value functions and additive functions, Choquet integral, and coupled with stochastic ordinal regression as well. So, now the second way of aggregation. The second way of aggregation was the outranking relation, and I already started to explain you that this is attractive because it permits to model incomparability. And the construction of the outranking relation proceeds through so-called concordance and discordance test. Concordance test is testing which criteria in the family are in favor of a hypothesis that A is at least as good as B. And for this credibility of the participation of the criterion I in the coalition of concordant criteria, we use so-called concordant index. And this concordance index is defined in this way as you see on the screen. Depending on the difference between A and B, the concordance index is increasing from 0 to 1. And then we have discordance index. Concordance indices are aggregated together, and we check if among the criteria from the opposition, there is no one which would say, no, the hypothesis of outranking should be abandoned, because on this opposite criterion, we have an advantage of B over A, which is greater than veto threshold. And then, when a pair is passing both concordance and discordance test, the outranking relation is true. And it can be represented as a graph. And the exploitation of this graph is the last stage. For example, if we would look for the kernel in this graph, the kernel will give the best and diversified actions which are forming the set of best actions. However, we wish to use ordinal regression and even robust ordinal regression also for outranking relation. And we hided the weight W in a function psi, which is replacing now the function C, the concordance index. And we are expecting from the decision maker the holistic preference information telling A is outranking B, or C is not outranking D. And again, we are able to draw constraints which are delimiting the passage of the function psi, the concordance function. So this is a little bit more complicated mathematical programming problem, again with 0-1 variables and big M, to model expressions A outranks or B does not outrank C, and to find the necessary outranking relation and possible outranking relation, we again use a simple mathematical programming problem, and we are getting necessary outranking, contrary necessary outranking, and in the graph we are counting in favor of an action X the necessary outranking from this X to others, and contrary necessary outranking from others to X, and as a weakness the necessary outranking from others to X, and the opposite outranking, the contrary outranking from X to others. And we are getting so-called net flow score. So here is an example which is hardly visible, but again for very scarce preference information, which is over this small guy. So we have the necessary outranking in the matrix. If the guy adds some pairwise comparisons, it is becoming richer. And the graph is like that. So the kernel is discriminating D and F as the best actions, and the net flow score ranking is giving the order. And finally, decision rule preference model. Decision rules, as to the syntax, I presented this at the beginning. So this is the syntax for classification, and this is the syntax for choice and ranking, so including pairwise comparisons with respect to intensity of preference if the criteria have cardinal scales, or if ordinal scales will take into account pairs of evaluations. And then we have in conclusion some preference relation, for example, outranking and the lack of outranking. To use this model, it is very useful to rely on rough set theory. Why? Because rough set theory is permitting to handle inconsistent information. What is inconsistent information in the word of multi-criteria decision making? Inconsistent is the information violating dominance. And when you ask, is it possible that people violate dominance? Of course, because there is not enough attributes, for example, criteria to compare to actions, and according to the knowledge of experts, the object dominating another object will not be considered better. Yes. So if we have such a realistic preference information violating dominance or inconsistency, as in the basic rough set theory, we need to structure the data prior to induction of decision rules. And in case of multiple criteria decision, the structuring cannot be done like in the basic rough set theory using indiscernibility relation, but we have to replace this relation by dominance relation. And the dominance principle says if X is at least as good as Y with respect to relevant criteria, then X should be assigned to a class not worse than Y. So this principle is substituting the indiscernibility principle, but still the mechanism of approximation is the same as in the basic theory of Clay-Zdzisław-Paula. The dominance-based if-then rules are attractive for at least 3 reasons. They give account of the most complex interactions between attributes. They can handle both attributes, nominal and also ordinal. They are non-compensatory, like additive utilities or even Choquet integral. And they accept ordinal evaluations only without transforming the scales into cardinal ones. Each rule is like a scenario of a causal relationship between evaluations on a subset of attributes and a comprehensive judgment. So they are also explanatory models of decision. Here I'm giving a very simple example again with 2 dimensions only. So we have, for example, 8 solutions presented to decision maker, and those objectives characterizing these solutions should be minimized. And we ask the decision maker, please indicate which one is relatively good and which one is relatively bad solution. So if objective should be minimized, so there is one part of answer which is expected, x1, x2, 3, 4, 5, 8. So this is not surprising that 3 of them are good and 3 of them are bad. But however, 8 is considered good and 7 bad. Why? Is it an error? As I will show later, it serves in multi-objective optimization. In multi-objective optimization, we represent solutions in the objective space. However, each such solution has an anti-image in the variable space, in the decision space. And for an expert who is looking at the evaluation of the solutions, not only in the objective space, but also in the decision space, 8 could be better than 8, that's 7. Because implementation of these solutions will be easier for him. There are some hidden objectives which are not analytically represented. So such an information is not surprising. And we are able to approximate them with the dominance cones and define lower and upper approximations and induce rules later from those lower and upper approximations. And from lower we will get certain rules, and from upper we will get probabilistic possible rules. I will end now with a few examples of applications. So all those applications will concern the rule model. First application that was implemented in practice was in the emergency room of a pediatric hospital in Ottawa, where non-qualified surgeons, so intern or a nurse, is making a decision if the young patient coming with abdominal pain should be released home, kept for observation, or the surgeon should be called, which is costly for the hospital, even if this is a false alarm. So we gathered more than 600 examples of judgments by surgeon doctors from several hospitals in Canada, and we implemented the system based on rules on the light platform, which was PDA. Then they required other diseases of children, scrotal pain, asthma, etc. So it is still a living application. The second application, which I would like to mention, this ended 2 years ago, This was auto-loan fraud detection using dominance-based rough set approach. And in the data set, we had 26,000 observations of a bank, among which only 405 were fraud events. And we made experiments comparing our approach with random forest and SVM, and especially for class fraud, there was a big advantage of the dominance-based rough set approach over the statistical approaches, even if for them some special tricks usual for unbalanced data were used. And moreover, what is the advantage of decision rules is that they are exemplifying situations. So first rule, 10th rules are showing scenarios of a possible fraud. Also, it is possible using a special analysis of attributes using Bayesian confirmation measures to evaluate the added values of attributes in the classification. And in this way you can assess the relevance of attributes in the whole range of attributes. Usually people coming to analysts bring too many attributes, and the feature selection could be, for example, like that. The third application is on the data concerning customer churn prediction. And we analyzed 10,000 customers, 8,000 exciting the bank, and 2,000 loyal. And this data set had many missing values. So in this case also our approach was adapted. And you see that the decision rules are showing also clear advices to manager what are the reasons of exciting customers. And the last application I would like to show you is a very recent one. It is a use of decision rules as a preference model in multi-objective optimization. Multi-objective optimization consists in maximizing or minimizing a vector of real valued function subject to constraints which in general is like that. And probably many of you know that at the beginning of the century the evolutionary algorithms have shown a great capacity of representing the approximation of so-called Pareto front. Pareto front is the set of non-dominated solutions in the objective space, and this result is then submitted to decision makers, to engineers, or to other users who are expected to select the best compromise solution. Yes, because this is a variation of solutions over 2, 3, 4, 5, 7 objective functions. So while it is easy to do it on 2 objectives, starting from 3, it is becoming a problem. So a wiser approach consists in putting the decision maker in the loop of interaction, gathering some partial preference information, guiding the search of the most interesting part of the Pareto front. Just like that, for example. And in the context of evolutionary algorithms, where is the place where the preference model can play a role in getting closer to the interesting part? This is at the stage of crossover and mating selection, because what you see in red, the ranking of solution by a preference model can make the convergence in the evolutionary steps. A very interesting framework for such an evolutionary algorithm was given by the algorithm called NSG2. So it is using so-called dominance ranking for the ordering of parents. However, this is a very I would not say, this is not negative, primitive, so simple ranking, which is a dominance ranking. Just first choose in the population the non-dominated set, then the second layer, etc. And within the front, so the layer, order the solutions according to so-called crowding distance, so that the most spread as possible. However, we adopted this framework to introduce some preference information in the interactive loop. And then the preference model is the set of if-then decision rules, and the classification concerns only a few solutions from the current population. And I may now reuse my example, and if the decision maker would classify these 8 possible solutions from the current population, then from them decision rules could be induced, either certain or possible, and then we would calculate the score for each solution in the population, representing how many good rules are matching this solution. And then the ordering of solutions within the front would be according to this score. And then in France, the solutions are ordered according to our score, and evolution continues. So in our case, decision maker is inquired about the classification of the sample of solutions, not every iteration, because evolutionary algorithm may have 600, 1,000 iterations. However, every 30, every 40, every 50 iterations, the decision maker is asked for such a simple preference information. So in case of continuous problems on the benchmark or combinatorial problem, our method worked very well. And what is the advantage of using rules? The advantage, I will not have time to go in detail of this example, but taking again a two-dimensional example, we can see that we are able to represent the preference model coming from the classification of decision maker by decision rules. And decision rules are translating, are summarizing the information just provided by the decision maker. So the decision maker is not giving this preference information in blind, but looks at the consequence in terms of decision rules. And this is very, very instructive. So thank you very much for your attention. What I tried to present was a robust ordinal regression paradigm for all 3 types of aggregation functions, of ways of aggregation, and I think that this robust ordinal regression inscribed in full in the European school of decision making represented by the mentioned Bernard Drouin. Thank you very much.
We have time for 1 or 2 questions. Ivan, yes, please.
Thank you very much. So thank you very much for your very provocative presentation. And I believe that compulsions and preference are very important part of decision theory and decision problems. My question to you is about scoring. How each object suits to the requirements or doesn't suit to the requirements from the interval of 0 to 1. Also, how if we have just one object to evaluate, it's not always to compare. Or if we compare, we can compare 4 objects, but all of them are very bad. Or all of them are very good, but not affordable.
Of course.
So please.
Yes, yes. So in your short question, there are several aspects. So first of all, the score. So what I try to say, I want to avoid such a simple scoring that every action is getting a single score. Yes, we are rather trying to produce models which say more than a score, because a score, a real valued function, will be also useful for making comparisons between, as you say, two actions, yes? But if you have one, so it will not evaluate them, yes? Because it is uncomparable with others. However, when you express the preferences in other terms, in decision rules, then you are getting scenarios of causal relationship between evaluations on particular and not all, but subsets of criteria and the overall evaluations. And of course, many people do not like more complicated, let's say, I would say more faithful models, because they say, oh, real numbers are, without discussion, solving the problems. However, we are coming to those composite indicators, to these scores, through very strong simplifications. For example, in medicine, the medical score for a disease is aggregating a lot of heterogeneous components. The blood pressure, number of white cells, and many, many others. And this is all synthesized to score 5, 6, 7 in the 0 to 10 score. The Nutri-score in food, now on many products you do not see that there is so much sugar, so much other ingredients, very dangerous, E, etc. But is it Nutri-score B, A, or C? And the companies, they know how the algorithm works, and they put as much sugar, for example, as possible according to this algorithm. And you don't know, because this ABC is obscure. So this is why I'm advocating for models which are explanatory.
If I may add just a moment. So what you mentioned now in medicine, I think it's a much more problem of simplification and oversimplification in aggregation.
Yes.
But there are models with very strong developed theory of aggregators, even with 15 levels or 23 levels, and with endness and overness how to do that. By that, our scoring could be very fine and taking into account more than hundreds of parameters, giving a real score of the object.
But this is mathematics, and there are infinity of O-ring or other operators which can be used. And which one is a good one?
I will give you one reference for mathematics that really mimics real logic of human reasoning.
So I would not say so quickly that we are able to mimic the human reasoning using one method. Believe me that in operational research as an editor, I'm getting a lot of papers proposing aggregation which is the right one. But after publishing one, I'm getting another paper criticizing the previous one, because in this aggregation operator there could be some change, and there is an infinity of operators, and such a battle could continue without the end. So practical verification is very important. Thank you.
Thank you. Thank you very much, Roman.